Okay, I think we're up and running now. I hope. Uh, we'll make sure if I don't have good audio or if you guys can't hear me, go ahead and leave a message in the comments. Otherwise, I think we'll get started here. Trying a new side by side, so it lets you see me a little bit better. I did push a couple of new things out on GitHub, so if you haven't joined these classes before, and this is your first one, github.com/08malooz/software sessions is the place to go. And there's a new project out there called Pointers. So if you want to download that repo, there's nothing much in the project. I basically handled the setup stuff we did yesterday, removing the precompiled headers and that sort of thing, and setting everything for the different builds. But that's up there. So go ahead and take a look at that and pull it down and get ready. As always, I'm posting sort of content and comments and all that right here on my blog. So day 2's page, similar day 1 has some links to references, has the link to GitHub. Also, if you want to contact me, that sort of thing, that's all listed right here. So figured I would just remind everyone that while they get the code coming down, and we'll go from there. So cool. Well, I'm going to close that out. I don't need those tabs. And I'll jump on over here to just my desktop, and I'll pull up Visual Studio. So today we're going to talk about sort of the powerhouse of C++ and C, and that is this concept of pointers and sort of direct memory management. So what I have here is the same project that is up there on GitHub. So if you clone that down, you'll be good to go. Otherwise, you can create a new project. I just removed the precompile headers like we did yesterday. If you have questions on that, you can see day 1's video. It's up there now. It should be done processing. I think it was done processing within like half an hour, an hour of it recording yesterday. So that should be up there. You can take a look at that and how to remove them. But yeah, this is the project we're going to start with, and we're going to talk about pointers. Like I said, pointers are the powerhouse of these languages. And what do we mean by pointers? Well, yesterday we created some functions and we moved some data around and had some variables. And basically every time we passed those values around, we were actually copying them. And copying data can be very, very inefficient, especially if you're trying to operate on data somewhere. Copying it 5 times, then having to recopy everything back can be kind of annoying, and it can be slow. From a computing standpoint, the slowest part of a modern computer is really the memory side. We can execute billions of instructions, but keeping that processor fed with memory is usually where we run into things. So like, this computer here has some very, very fast memory on it, and it has a lot of it because ideally I don't want to have to hit storage. That would be even slower. So one of the sort of things that other languages like Python and C# or Java might do for you is they'll handle the memory management for you, and they'll take a best guess, and they'll do this thing called garbage collection every once in a while to sort of clean up memory that is just sort of floating there or copied or whatever. We don't have that luxury in C and C++. We get to be a lot more explicit about that. And while it might be a little bit more painful to develop like that, it does give us greater flexibility and control as the developer to do things when it makes sense. Nothing sucks more than having Java do garbage collection right in the middle of something that's computationally very intensive. As where in C and C++ we can sort of control that. And yes, there are ways in other languages to force it, but you don't want to be reliant on that to really make your application perform. So just going from there. Also trying out a new setup here, side by side, so you can hopefully see my desktop and me at the same time. So I figured I'd jump to this when I'm doing more of this talking stuff. So we're going to get back into the code here. So I'll jump back over to that screen first. So first off, let's start off by making a variable. In this case, we're going to call it int a, because I'm very original. I'm going to say it equals 0. I'm going to delete this hello world line. You can keep it if you like. It's just sort of in my way. I now want to do some stuff with int a. So we need to learn some syntax for this. So the first thing is that we're going to create another int, and then we're going to put a star and then b. So what int star means, and some people put the spaces like this, some people keep the star closer to the data type to sort of say what it is. Some people prefer to put the star near the variable. C and C++ are not based off of spaces, unlike Python, so you can sort of put it wherever you want. I'll leave it closer to the data type. So this would be a variable with a value of 0. And then this would be a pointer. And I'm just going to set this equal to null pointer. Pointer to an int with a value of null pointer. Null pointer is also 0. It's a type def thing. And if you're ever curious, you can actually click through here and you can start seeing what some of these things are. F12 is that way to sort of look up hierarchy in Visual Studio. So B is a null pointer. So there we go. So I'm just going to put a line here, print f, because I include my standard io.h, value of a, %d, value of b, %d, pass it a and b. Here we go. Actually, we can't just pass it b. And why is that? Because we said b is a pointer, so b has to point to something. So we need to dereference our pointer. So that's that key word there, dereference. And that basically means instead of saying we want the value that you're pointing at, instead of saying we want what you're pointing at, we want the value of what you're pointing at. So that's sort of the concept of a pointer, right? It's pointing to another value. We want the value that you're pointing at. So in this case, I'll put star b. And if we go and we run this, and then I'll put a return 0 on the end because it's a main function. Here we go. I'll just set to go to the breakpoint. Oh, we threw an exception. And look at that. The reason why is b was a null pointer. So that means that we're trying to see the value of something that we don't know what it is. We can actually continue through that exception, and it's just going to keep yelling at us because a null pointer exception is a very big thing in C and C++. So we need to set some value to that null pointer. Well, why don't we just make b point to a? So to do that, we're going to say b equals, and then we're going to put an ampersand. Ampersand stands for the address. So that's basically the value of a pointer. A pointer would contain an address to another memory location. So we'll say to the address of a. So if we go and we do this now, everything builds. We get to our value there. And a and b both have a value of 0. Cool. I'll stop out of that. Now if I go back and I remove this star from a and b, and I'll put this line just before. So now we're not treating b anymore as a pointer. We're not trying to dereference it as we were. Let's take a look at what value we get here. So here we go. I'm going to step over that. So we see that they're both equal to 0 here, and that makes sense because a null pointer is effectively a value of 0. And then when we say that b is the value of a, I forgot my new lines there, you'll see that we get this negative 2998943 whatever, right? That's a memory address. That is some address in the banks of memory on my computer. And that is the value of b. So it's now pointing to that value. So I'll exit out of this, and we'll be a little bit more descriptive, and I'll include my value of b, value of b. There we go. I'll put printf in here to say what I'm going to do as well. Printf. And just to prove us out, right, I'll take the same line And I'll set A to be the address of A. So this would be the pointer to A. And the value of B. So these two should be the same. So again, just to recap, what we've done is we've created just a basic integer. We've created a pointer. And a pointer, remember, points to a memory address. So it holds some address value, and we initialized it to 0. We then printed this out so we can see it. We then set the value of that pointer to the address of A, that integer A that we created. We don't know what that address is. We didn't pick that address. The computer assigns it when you declare int A, and we just got the value of that and put it in B. So now we have the value of A and B, where A is still an integer, and B is a pointer to that integer. And just to prove that out, actually, I'll change this to address of A. We then decide to print the address of A and the value B. So here we go. Let's take a look through this. So I'll click through here. I think we know what we're doing right there is we just assign the value. We print that. We see that has a value of 0, and B has a completely different value than we got last time. Those addresses, like I said, are assigned when the computer goes to run that command. So, I don't get to pick it. It is what it is. So there we go. And then if we look at this again, though, we'll see that the two numbers match. And that makes sense, right? The address of A equals the value of B. That makes sense because we assigned B to the address of A back on this line. So that makes sense, and our program is running well. Let's add another printf here. I'm going to say setting the value of to 7. So we'll set the value of A to 7 next. So A equals 7. And I'm just going to copy down this printf line right after it. And let me space this out just so it's a little bit easier for everyone to follow. There you go. Sometimes spaces, like I said, they don't do anything in here, but it just makes it easier to read. So here we go. We are now setting the value of A to 7, which means A is going to change. It should. B should not change because B points to that address. So let's take a look at this again. And let's do one other thing. Let's see if we can get the value of B, or the value at address B. And to do this, like I said earlier, we're going to dereference the pointer. Remember that's what gave us that null pointer exception in the beginning, which is one of those errors that you really can't get around. Dereferencing that pointer can be very dangerous, but you're basically going to get the value or set the value at that point. So here we go. I'm going to jump it down to here. We'll run our code. Should see this makes sense. Look, again, completely different address. That makes sense. And now we go and we set the value of A to 7. Good. And the value of B didn't change because B is pointing to A. So its value didn't change. And to prove that it's actually pointing to A and that I'm not just making this up, you'll see now that the value of A is 7 and the value at address that's given by B is also 7. That makes sense. So this means we have multiple ways to set that memory location that is given, that is int A. So maybe I'm going to set the value at address B to 8 in my new line in there. So then this would be star B. Remember that dereferences our pointer. That says the value at that address equals 8. Cool. So let's print off what A and B are now. So in theory, A should change from 7 to 8 if this logic holds true. So why don't we try it out? So we'll build it up here. Here we go. We've printed out. Set the value of B to 8. And look, the value of A is now 8. And we set that by using the dereference pointer that is provided to us by B. So as you can see, this can be really, really powerful and also very, very dangerous. So I'm going to actually save this here. I'm going to call this pointer intro. This is going to be B equals the address. And I am going to throw this up there on GitHub so everyone can follow along. Of variable. There you go. So if you're following along on GitHub, you should have access to this. Uh-oh. I have something. There we go. I think I might have edited a file up there without pulling it down locally. There we go. That pushed. So, yeah, one thing on Git is you're supposed to pull before you push. Usually I'm the only one writing to something, and I might tweak something from another computer in between. So, but that should be up there now. So I'm just going to check the chat here, see if we have anyone voicing any concerns or anything here. I don't see any concerns. Let's leave a comment there, see if everyone's doing good. But with that, let's keep going then. It seems like everyone's following along. Okay, so now we have done, probably the hardest thing in C and C++ right now is this idea of using pointers and doing this sort of simple, assign and value change. But we can also use pointers to handle memory. And that's probably where things get a little bit more interesting. And this is one of those intricacies between C and C++. I'm going to give it to you in the C way today. And we'll talk about the C++ way tomorrow, just to keep things simple. So let's dive back into this. I'm just going to go to my desktop only now, just because I'm going to be getting a little bit longer. I'm going to create another pointer here, and I'm going to call it an int star. I'm going to name it array. So maybe not array, that's a keyword. Try memblock. Make it up there. So I make a pointer to an integer known as a memblock. Well, you can set up blocks of memory of different types by doing something called a malloc and using it as a pointer. So if I want to set memblock equal to something, or set it equal to a block of memory, I can do memblock equals, and then I usually have to cast it to an int star, because it's going to return just a generic pointer, malloc. So malloc is a C function that basically stands for memory allocation. And we got to give it some parameters here. It really just wants a size, and it's going to take a size in bytes. But in this case, I'm going to say I want to make an array of integers. So I'll put size of, which is a very handy C function. I can put int. So this is now doesn't matter what computer I'm running it on. Could be 64-bit, could be 32-bit, could be Windows, could be Linux. The size of really just lets it at runtime figure that out. And let's say I want to make this be 100 elements So 100 integers in this array, or in this block of memory. So the computer is going to do that, and then before you exit, you need to clean up this memory. Remember how we said, C and C++ isn't like Java in that regard where it handles it for you? We have to do it. If we don't do it, it's called a memory leak. Now you can be lazy and not clean it up if your program exits. For example, this particular program, it's simple enough. I probably don't need to clean up the memory. It's not the end of the world. But if I'm writing a larger interconnected program, you generally want to clean up that memory when you're done. When something goes out of scope or gets deleted, you can do that. But if you don't, it's called a memory leak. And they're generally bad because they can consume all the memory on your computer. So, memory leaks, not great, but sometimes it's a problem that is really drastic and you need to handle it, especially if you're looping and you're creating memory and you're not freeing it inside the loop. But sometimes if it's a small application, it's practically not an issue. So to clean up this memory, we use a command called free, and then we just pass it the pointer. So in this case, it'd be memblock. So this is going to then clean up that code. Now, let's say I want to set the value of memblock. I have a couple of different options. I can say, we can do it the pointer way. I can say star memblock equals 5. That's one way to do it. So that will say the first element of memblock equals 5. And here we can just do that for an example here. Printf. Memblock. It's going to be %d. New line. We'll say memblock star. Oh, not memblock star, star memblock. There we go. So that'll set that first value of memblock to 5. That's one way to do it. I'm going to copy this line. We can do it another way. If you've programmed in a different language, you might like this approach better. This is my preferred approach. Memblock of 0 equals 15. So this is one way to do it, much like how you would index an array. So you can do it that way. And let's take a look through these. So I will go down here, and we will run. Now, it should be noted that this malloc is a dynamic memory allocation versus a static memory allocation. You can declare a static block of memory when your program starts, and that's handled by the compiler and makes life a little bit easier. We're mainly focused, and you don't need to free it or anything. It knows when it goes out of scope. I'm focusing here on the dynamic memory allocations, but I'll add a static one as well. But if we look at our code here, nothing happens when we call a malloc. There's no visible code. We just created something here. But we take a look at the value of memblock. It's 5. We now set it to 15. And we look at it again, and we can see that we can access it either way. So that's really nifty. And that's just one way to access that. We could also say we want to look at the 10th integer. So I'll save this line. So we have a couple of different options here. I could create another, I could say memblock of 10 equals 1000. And I can go over here and say memblock of 10. That's one way to do it. Another way, if you want to do it pointer-wise, and this is sometimes handy for loops, is to do it by a pointer offset. So I can say memblock, and I can actually add an offset to it. So I can do an offset in bytes. I can do an offset, in lots of different types. So I could say memblock plus, I don't know, plus equals, 10. And then I can go equals 1500. So here we go, and we'll hit our mem block of 10 equals 1000, and we'll see that here. And then I'll go down here and I'll add 10 to the pointer mem block, and you'll see that I had a little mistake there. I still kept mem block indexing at the 10th value. I should not have done that. I should use it by the pointer. There we go. And if you see there, now the value at mem block is 1500. If I wanted it to express it a different way, if I still wanted to express it with this mem block of 10, I would then have to do mem block minus equals 10. So I'll come back down here, and we'll run that again. I'll go ahead and step over, and you'll see it's still 1500. This is called pointer arithmetic, and it is a great, great way to sort of speed up computation. Rather than copying something or trying to figure out where something is and iterating over it, if you can just jump to that location in memory by adding to a pointer, that's really handy. It's not recommended to mix them like we've been doing here. I'm mixing it mainly just to show you them both side by side. But you can totally add values to pointers and have it index and that sort of thing. Now, remember I said you can add different amounts to a pointer. The pointer's type dictates how much you're adding when you add, say, 10. So because in this particular case we declared memblock as a int star up here, that int star says that every value that we add to that pointer is treated as an integer in terms of its offset, which on this machine is going to be 4 bytes. So it does that math for me. But if it was a char, on this particular computer, a char is going to be 1 byte. So every time I add 1, I'd be adding 1 byte to that offset. So that is a really helpful thing to do when you go to actually, write complex programs, is start, addressing things and doing pointer arithmetic. Remember I said computation is essentially free. So if you're trying to find something in a list, or you're trying to do something like that, it's much faster to just get the pointer to the memory, do the math to find out where the value should be, and go check the value than it is to copy the entire thing over and then loop over it and try and see and find the value. So that's how this is sort of built up. Figured I would check back over here, make sure I'm not missing any questions. Seems like we're not. Cool. I can also do something like an int star star, as you're seeing here, and I'll call this mem block pointer. So this would be a pointer to a pointer. Think of the movie Inception here, full-on sort of thing, right? We can have pointers to pointers. That's typically how we try not to copy arrays. Because if I gave it the, the direct pointer to the first value, that might be interpreted one way or processed one way. So a pointer to a pointer is sometimes a little better, which does mean you do have to dereference it to use it. So if I want to say, if I want this to be the pointer to the memblock pointer, I'll go down here and add new line. It dawns on me you're probably not going to be able to see that much longer, so I'll turn off that video. Memblock pointer equals the address of memblock. So now, if I want to set the value of memblock, so if I want to set the value of the 100th element, or maybe the 50th element, you would do something like this to dereference, what essentially is the 50th element. equals 7. And then I could print out there we go. And if we print it out, we look at our code. Ooh, that's not correct. So I messed up here. Like I said, you're getting this live. So I guess this is gonna, the brackets here are gonna dereference first, I guess. So this might be a case where you need to do parentheses, and I'm sure someone was screaming at their screen watching this, to have that same function execute correctly. And there we go. So yeah, it seems like it assumed to dereference the entire expression instead of that first part. So there we go. And you can mix it like that. Like I said, because of errors like that and things that I just messed up live, you know, this stuff is one, hard, and two, you generally don't mix it. It's considered sort of bad practice to mix them. If you're going to treat something as an array and use sort of the array notation, keep it that way, versus if you're going to, you know, treat something as a pointer, treat it as a pointer. So cool. So now we have our nice little bit of pointers here. I'm gonna put in a there we go. Now let's say we want to make our program ever so much more complex. We want to have another function. Now remember, we added those functions before, those declarations before, and we had some issues with that. You know, we had to make sure that we declared everything before the main function, which we're starting to get a really big main function now, and then we implemented it beforehand, or we had to implement it before the main function and all that jazz. It's kind of a pain. We sort of touched on the concept of a header file when I had to include standard I/O before. But let's actually play with these header files a bit, because they're similar to how pointers are used and how you can point to another, essentially, bit of code somewhere out in the ether. So I'm going to create a new header file. Actually, before I do that, let me make sure I get this up in GitHub for anyone following along. There we go, for everyone following along. If you want to clone that down. There you go. I'm now going to add a new header file. So new item. And see, it's got header here. And it's going to add it to the pointers folder. And I'm going to name this pointer functions.h. Generally, header files match the name of their corresponding C++ or C files. So let's, while we're at it, add another C class, or C++ file. I'm just going to call this pointer functions. We're still going to write just C code in here. You know, like I said, we'll talk about the differences tomorrow. But leaving it name.cpp is fine for all intensive purposes. So there we go. So the first thing we need to do is we need to include in our C++ file pointer functions.h. It's really helpful when it does that. And I'm going to also include this there we go. Usually you use quotes when you reference your own header files, so just something to do there. So in this file here, you notice it has a pragma once. This is to keep the header file from being reloaded potentially multiple times. As you get to bigger, more complex applications, every time you use a include, it will load that header file. And conceivably, if I have one header file that includes another header file, and I include it directly because it's a big code base and I lost track of that, you could run into things being declared in multiple places, and then you don't know where something is. So let's say we had a global variable in here. So we'll have a global int. This value might be used in this file, and if I want to get a pointer to that global int from this particular file from pointers.cpp, and I included pointer functions twice, the compiler wouldn't know which one to actually talk to. So that's why it can be problematic to have multiple headers included multiple times. So the pragma once helps with that. But what's cool about this header file is we can also declare function names in the header file. So let's say I want to make a function here that is going to be a void inc global vars. And it just increments global variables, and it will take a pointer, let's use a pointer, to an integer to increment them by. To use those, So cool, we now have this file. Now what's nifty is that Visual Studio is smart and says, hey, you need to declare this file and you should do it somewhere, and it says, oh, you can declare it in the CPP. So it pops up even this nice window. I can just go over to the CPP file, and it declared it there nicely for me. So this function will basically say our global var, or global val, plus equals the value at, remember, it's a pointer, it's an int star coming in, it's a pointer, so the value at, which means we put the star out in front, value to increment. Sounds good, right? Let's go use this in our pointers function. Cool. So here we go. We're going to use our header file function. We're going to say global val equals 0. And then we're going to make an integer and call this increment. Say we'll set it to 1 to start with. And then we're going to call that function. So if we go back over here, it's inc global vars. So if I call, and notice how Visual Studio even detects it because we're using that header file. And then in between the parentheses, I need to give it the address of the value inc. And I'm going to print here our global value. So cool. So let's head down here. I'm going to run it, let it compile. I had some build errors. What were my build errors? Let's find out what these are. I have 2 errors. So remember I said if you declare something, it might be included and declared twice. In this case it was. It was already defined inside of one of these 2 functions. So in this case I'm going to do what's called extern, which means it's external to this header file. There we go, extern. And I'm going to declare this guy inside of my pointers functions.h. And that should resolve that. So basically when pointers.cpp goes to use global val, it'll find it in the header file, and the header file is going to say, I don't actually have the definition, I'm just a link to it, and it will find it, the compiler will find it inside pointerfunctions.cpp. There we go. That seemed to work pretty well. So now we get to this inc global vars, so we can pass it in. And we'll see that we are going to increment global val by 1. Cool. Go back, and then we'll print it out. And you'll see that global val is 1. So if we wanted to put in a loop here, yesterday we used a for loop. Today, why don't we use a while loop? While global value is less than, say, 15, just because I want to have it print a lot. There we go. And if we go to run this, we see global val counting up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Cool. Now we can also play with this a bit too, and we can say we want to change the value of increment. So why don't we say so we're also going to double the value of increment. So to do this, we're going to say the value at value to increment times equals 2. Now you're probably wondering, how are we going to change this value? And that's a great question. So yesterday we talked about passing in these parameters, and you really can't change them once you pass them in. It won't affect the calling function, right? If you pass in a pointer, you can't change the pointer itself to affect the calling function, but you can change the value that it's pointing to. So because we are not passing in the value inc directly, because we're not passing in inc directly, but the memory address of where it's at, I can then access that and actually change its value. So let's actually run this and see what we get. If we look at our code now, the value of global val is in fact 15, but look at how our incrementing goes. It went 1, 3, 7, then the next one would be 8, 15, etc. So if we can step through this, I'll exit out. Let's step through this now and see what's going on. So the first time this is called, we call into global val, and we increment it, so it becomes 1, right? That happened before. We're good. The next time, though, we have this memory address, and you can actually check in Visual Studio. It'll actually go find that memory address and tell you what it is there. You'll see that it says it's a value of 1. If I step over that now, and I use that same thing, it says the value is now 2. So it has incremented it, or it has doubled it. And go back here, prints it out, happy day. And if we look here, our value of inc is in fact 2. So it did add a value to that. Even though that is a local variable to this particular function, because we're giving the pointer to it to another function, it can modify it. And this is a problem. This is a big problem, when you're writing code, and because you can have potentially someone else modify your memory out in your computer, or worse yet, you can accidentally modify memory inside your computer. This is what causes a lot of those blue screens of death that everyone sees. Is usually it's some pointers writing to some place it shouldn't be, and that's what's going on here. Is we're allowing it to happen, but if you don't know where you're writing to, you could be giving it garbage data, and that is a major sort of gotcha in C and C++. And it's probably things like this that scare people away, but the burden is on the developer. It's on us to sort of think about these things. And if you just, whenever you try to process your code, there's some really sort of good style tips that you can use to mitigate these particular instances. For example, when I write a library, I never let anyone talk to me and control a pointer inside of my library. I will always have them copy it in, or do that sort of thing. Yes, it's a little bit more overhead, but it greatly simplifies the problem and provides that level of security. It closes that potential exploit hole. The other thing that you can do to avoid this when you're coding is use a very important keyword called const. So const basically means that whatever you're describing is a constant. So I'm going to go back to desktop only here so you can see it. So I added const to this line. So constant, this is basically saying constant integer inc equals 1. If it's a constant, that means we should not be able to change it at all. So if I go to build this, I should have a build error. So if I go look at this build error, you'll see that's an argument of type const is incompatible with type int star. Void global cannot convert argument from const int star to int star. So it's basically saying that it can't pass this particular value over. And it's saying that this needs to be a const int star. Okay, we can pass that. Right? Let's fix that. This should work, right? No, it didn't, but I fixed what it said. It's because you also can't assign that variable value. So it's a nice way to sort of catch you on two different levels. You know, this is saying that this is a pointer to a constant integer, right? That's what the star means as a pointer. It's an integer, which is the title int, and const means that it's constant. So this would be a pointer to a constant integer. And the first time it was saying, the first error that you saw was that I was trying to pass a pointer to a constant integer, which the compiler treats differently as just a regular pointer to an integer, which is obviously a problem, and it caught that. And then when I fixed that problem, it then said, whoa, 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 you can't assign values to that. So const is a pretty important, term here. I'm just going to comment this out and say, so it's one way to have the compiler check you. And this is really, really handy to sort of mitigate some of those problems. Like I said, there's the stigma that C and C++ are very, very complicated in this regard. But if you use some of these keywords like const, or you stick to things that you're familiar with, like using the array notation for blocks of memory, and you think about them as arrays, can greatly simplify your coding experience and make life a lot easier. So I am going to go pop this back up on GitHub now because we've added a whole bunch of stuff. So I got to add pointers.cpp. Oh, git add pointers.cpp. What don't you like about me? There we go. VCX. Project filters. And then add the pointer functions. There we go. Cool. I'm going to make another copy of this one too before I commit up there and remove the const. I'm going to call this one const. I will remove that. And remove that. And if I go over here to inc global vars, I'll call this one const inc global vars. There we go. Make sure it builds before we do that. It does. This should go 15 times. It does. We exit just fine. Cool. You make sure There we go. That's up there. Now header files can actually do a bit more than this. Header files can actually hold functions. It's generally not something you want to put in a header file, just because header files holding functions, can lead to them being redeclared, can lead to all sorts of stuff like that. And it's good to sort of separate things out, but sometimes you have a need to. So maybe I just want to make a really, really simple function here that is, it returns an integer, and it is just add 1. And it takes in a int a, and then I can just do return a plus 1. Super simple, right? Don't know why we would ever want this function, but whatever. And I can call this function just like I would over here. So int Andy, I'll name it after me, equals 5. Add 1. Andy. And then I can print cool. So this should just really do nothing terribly interesting other than, add 1 to the value of Andy. Yep, I had a build error there. So it ran into that same potential problem here where it's being included in more than one space, and having, those same sorts of, copy issues. So again, this is, one of those problems of why declaring things in header files can be a pain. What I'll do is I'll just remove it from this particular header file. We'll add a new one. Call it header and call it function header. There we go. Put that in there. And we'll just go up on top here. Pound include function header. There we go. There are ways to get around that, but it's a little bit more advanced than I really want to cover in this particular video, seeing as we're also coming up on sort of quitting time. So here we go. If we look at our value here, we say the value of Andy is 5. The value of Andy didn't change there, but if we say int return val equals that, put return val in there. Here we go. And we'll see the return val is 6. So that worked inside the header. So you can easily declare functions in headers. That's something you can do, especially if they're small and easy. This is commonly used in C++, and we'll see this tomorrow, where you're just trying to set up a getter or a setter for a class. Sometimes it's easier just to return everything there. The one other thing that you can do in headers that you can't do in C++ files is this concept of an inline function. Inline is an important keyword. Inline means that when this code is run, instead of calling this function and adding it to the call stack, the compiler just basically modifies it so you don't have an extra function call there. It just executes the code logically. And this is important if you want to do an inline function for speed or to minimize calls to your call stack. Sometimes you'll get into like recursion and you'll get like huge call stack overflows and stuff like that. That can be problems. So if you say inline, basically you're going to be executing instructions, and then rather than jumping over to a new instruction or to a new function and running it, It's just going to copy and paste everything in there and then just keep sort of going over it. It's similar to using a macro. We haven't really talked about macros yet, but macros are functions that you can define that get pasted in by the C preprocessor, which is probably a little bit beyond the scope of at least this first week of class. But it's similar to that concept, except for it's just actual code. And the big advantage of it being actual code is that you can actually debug it, and you can step into it, as where a macro you can't really debug because it's copied in after the debugger step. So if we go to run this now with the inline function, it should be the identical output, and we'll see that here. The return value is 6. It just reduced the call stack. And if we actually set this up, and I rerun it, here we go. I step into it. It does actually make a call on the call stack, but for debugging purposes. But in terms of code execution-wise, it's not actually doing all that overhead of copying all that memory and doing all that stuff. It's just actioning on it. So it does allow you to debug, like you could see that we could see in the call stack, and we could debug and step through it. It just doesn't force that actual memory allocation to happen on the back end. Now, one other thing that I want to cover here that I think would be cool. Remember when we said, make 100 ints? That's not terribly big, and we have this whole memory counter up here. Let's make this a lot bigger. So an integer is 4 bytes. So if we say make 2,000, right, that's going to be like, I don't know, 8,000 bytes, 8 kilobytes. That's kind of big. What if we said we wanted to make it bigger? Add a couple of zeros, right? Make it really big. When we go to run this, I'm sorry that I'm jumping around, you'll see that it's going to create a whole bunch of process memory. Do you see where it just skyrocketed there in the memory usage? So it has to get all that memory. Now we're operating on it. But basically what happens is when your program gets a malloc like that, where you get some giant block of memory, in this case 20 or 200,000 ints. So you can do the math, that's 800,000 bytes. So, 800 kilobytes. Yeah, that's kind of big. We can make it bigger. Add another couple zeros, right? And this can take a while for this function to execute, depending on what's running on your computer and how much memory you have. So that's one other thing that can affect things. So you can see, wow, we just sort of went huge consumption in terms of both processing power and memory. And this is all because of that malloc function. And it can actually take a while for malloc to get all of that memory for you to work on. And it can, be very, very inefficient in terms of its utilization and all that. So that's why I like to run computers with a lot more memory in them to handle that. And I also try to minimize mallocs in my code. I try to keep them, just in the few places that I absolutely need them. So just some food for thought in that regard, but figured I would share that with you as well. And just to be ornery, I'll set that value at 0.5000 just so it, there you go. It will typically try and optimize out some of this too. The compiler will, to minimize the overhead and all that. But and then it will free, and free also takes a little bit of, you can see the little processor peaks here where we need to allocate and deallocate the memory usage, and that's just that's just sort of part of the game of writing code, is consuming all that memory. So if I set this to memory usage, it should skyrocket here. Oh. So let me rerun this with the heap allocation active there. Nothing popped up. That's interesting. I haven't played with that debugger all that much, but yeah, anyway, we allocated a bunch of memory, and that can take time, can take minutes. You have to allocate a lot of memory, though, for this to be a problem. So, you know, that's on the order of kilobytes. That's sort of on the order of megabytes. You know, if I add, I think, like another 0 or 2, it might actually fail at that function, that it can't get that much memory. But you can see it's now working really, really hard. There we go. We just allocated 8 gigabytes of memory there. You know, so use 7.5 gigs. If you look at my CPU process counter here too, you'll see that it jumped up right there, and that was this program allocating, you know, 7.5 gigabytes of memory. And then what's really cool is if we step through this a bit, we do our work on it and whatever, right? We'll then free this memory, and it goes back down. And it goes down in real time. Like I said, this is all dynamics. You can see it actually going down right there. And you can see where it's stopped up in the profiler. So just some interesting ways that playing with, you know, memory can affect things. And that's why, you know, you may choose to do an inline function, is to save maybe some overhead of that memory, especially if you're doing something recursively. So sort of taking that all back to where we were. And if you notice, it also took like a full second to allocate all that memory. It took time, you know, and that's part of the fun, is, you know, it has to find that block of memory on your cards and let you, you know, play with it. So cool. So we've covered a lot so far. We've covered pointers and how we do that. We've covered, you know, the address of, dereferencing, creating pointers, and all that jazz. We've covered header files. We've covered memory allocation and freeing. So this is really sort of the bulk of the content that I wanted to get through today. We didn't have a lot of questions. It's been a very quiet chat. Just ask if there's any questions. See if anyone has anything that they want to say or share. But, you know, we've covered a lot of material. This stuff is not easy. It takes time, and you'll need to play with it. So, you know, I recommend trying a few times, and you'll pick up some good habits from dealing with the problems. You know, as you saw, I did this live, so there are some issues that pop up that, you know, I've done this now for over 10 years, you know, and there's still things that I forget to do every once in a while that trip me up. So, you know, we'll go from there. But I'll hang out here for a second. I'm going to add some comments to the code and then push it up to GitHub. See if anyone else has any questions on there, and then we'll end the stream. And I appreciate everyone who's been with me today. It appears we've had a peak of like 11 people. At least that's what the analytics are saying. So thank you folks for joining us. If you can't join it live, you know, I appreciate you watching this later. I did put in the description down below the link to day 1 in case you find this video out of order, as well as all the useful links that we, you know, had from last time. And we'll go from there. But yeah, I'm just going to add some comments to this. I'll switch probably back over to the other view so you can see them as I add them. And then if you have any questions, you know, give me a shout. But thanks for watching. Cool. That looks to be pushed up there. So everyone watching at home, feel free to pull this down. It's up on GitHub. Thanks for Michael watching, and I'm going to be powering this down. So thank you everyone for joining us on day 2. I'll be back tomorrow at 1 p.m. for day 3, and we'll see what else folks have. So thanks for joining me. Talk to you later. Bye-bye.